So this video is our second day of parametric equations. And this is going to give you a better idea of why we might use these equations or when we might use these equations. It's going to give you a little bit more insights to the graphs of some of these parametric equations, as well as some applications that can be pretty helpful. So the first example, example 1 here, we're given two parametric equations. Our function x in terms of t is defined to be x equals 2 sine of t, and then our function y defined in terms of t is y equals 3 cosine t. We're given the domain restriction on t 0 up to 2 pi. And we're asked to eliminate the parameter and write the corresponding rectangular equation. So I just want to remind you what that means, this idea of a corresponding rectangular equation. That means that we're going to take the relationship provided by our x of t equation and y of t equation, and we're going to write an equation in terms of just x and just y. Okay, and this is not immediately obvious in this example. So we have the function, or the parametric equation, x equals 2 sine t, and at first glance, really the only thing I feel like I can do is divide out the 2 to both sides and find that x over 2 is equal to sine t. But we're supposed to get rid of t. Right now, t is an argument to our trig function sine. So I feel like I'm a little bit stuck here, so I'm going to go ahead and focus on the y equals, or the y parameter, the parameter for y in terms of t. So y equals 3 cosine of t. And following kind of the same line of thought, I can divide out that multiplier to both sides and get y over 3 is equal to cosine of t. Now, I have not successfully eliminated the parameter t, but what I have done is I've rewritten these equations where it's just sine of t isolated on one side and cosine of t isolated on one side. And this is going to lead me to think about using some sine and cosine relationships. So I know that sine squared of t plus cosine squared of t is equal to 1. So this Pythagorean identity is kind of lurking in the background here. If I could come up with an expression for sine squared of t and an expression for cosine squared of t, I could add those and set them equal to 1. Notice I don't have that quite yet, right? I only have sine of t and cosine of t, but I can quickly square both sides. So if I square this first equation and square this second equation, I find that sine squared of t is equal to x squared over 4, right? So all I've done is I've taken that first relationship, that manipulation of our parameter x of t, and I've manipulated it. I've isolated the variable t inside that sine function, and now I've squared both sides. So notice we have x squared in our numerator, and we also have the 2 squared. That gives us the 4 in the denominator. Similarly, when I square that cosine t equation that came from our y of t parameter, I find that cosine squared of t is equal to y squared over 9. So what I've just done is I've done some manipulating that will allow me to replace the quantity sine squared t and cosine squared t in this Pythagorean identity. So instead of sine squared t, I can write x squared over 4, and instead of cosine squared t, I can write y squared over 9 and set that equal to 1. If you notice, I've created from these two parametric equations, I've created an equation in terms of x and y. This is a rectangular equation because it only contains x and y. And it's actually an equation that you guys have seen earlier in the year. This is the equation of an ellipse. Okay, and it might be fun to kind of look back into your notes to see what exactly that looks like. But big takeaway here is that Pythagorean identity of sine squared t plus cosine squared t equals 1. It's kind of lurking in the background. It's helping us connect these original parameters, the original manipulation of these parameters, into one single rectangular equation. Okay, so now we're going to do a little bit more work with these parametric equations defined by trigonometric expressions. We're going to look at the graphs. And I'm actually going to go ahead and go through two options here. One is going to kind of be a refresher on what we talked about last week, and then the other option is going to maybe solidify from some of the skills from example 1. Okay, but I'm going to just go through each of these one at a time. So our first option here would be create a table, right? That's our 4-column table that's going to, so we can create the table that will allow us to find our XY points and plot those. Okay, so this gives us a little bit of practice evaluating different points on our interval for t, and then plotting those on our XY grid. So as a reminder, our table starts with a column for t, then we leave space to write our x of t parameter, so x equals 2 sine of t in this case, and y equals 2 cosine of t. And then our last column is that ordered pair x comma y, the collection of the outputs from our second and third column given our different values of t. So in looking at our domain restriction on t, we know that we can include 0 and we can go up to 2 pi. Okay, and it's going to be important to carefully select points, right? We want to select certain values of t on this interval that are going to be easy to evaluate, and also simplify given the expressions that we have. So taking that into consideration, I'm going to go ahead and evaluate our x and y parameters at t equals 0. So when t equals 0, we're looking at 2 sine of 0, which is equal to 0, and 2 cosine of 0, which is equal to 2. And this gives us our first point that we'll plot of 0, 2. So x is 0, y is 2. So we have this point right up here. My next t value that I'm going to choose is pi over 2. If you want to, you are more than welcome to plug in pi over 4. I don't think that would be a bad idea. But I'm going to go ahead and jump to pi over 2 and analyze my x of t function there. So 2 sine of pi over 2. I know that that is going to give me an output value of 2. And then again, 2 cosine of pi over 2, and that will give me an output value of 0. So my next point is 2, 0. Next, I'm going to choose to evaluate pi. These are just nice radian values to plug into my sine of t and cosine t function, considering we have that multiplier of 2 out front. So 2 sine of pi is going to give us another value of 0. 2 cosine of pi will give us a value of -2. So we have the xy coordinate 0, -2, which will be right down here. Okay, and lastly, just to kind of finish off this shape, finish off this kind of analysis, I'm going to choose 3 pi over 2, and I'll find that 2 sine of 3 pi over 2 is equal to -2, and 2 cosine of 3 pi over 2 is equal to 0. So I have the next xy point of -2, 0. Okay, and I'll plot that here. So something to be aware of, just with playing with these points and some other radian values, we can go ahead and connect these points not in a straight line like that just tried to do, but actually in a circle. Okay, if you were to pick a radian value in between 0 and 2 pi, you would find that your points are kind of plotted along this arc. Okay, so it's really tempting, given the fact that I only chose these 4 points, to maybe connect it in a square, but that's not actually accurate. Okay, so if you want, I would encourage you to plug in a radian value between 0 and pi over 2 and kind of give yourself an idea of where this arc is kind of falling. So the last thing that we need to do is add our directional arrows. So I'm going to follow the order of the color points that I plotted here in the table around my circle to show anyone who's reading this graph that we are moving in this direction. Okay, and that gives me the complete graph of our parametric equations, x equals 2 sine t and y equals 2 cosine t, using this first option. Okay, our second option is actually, so we have a second option, another way that we can graph these, and that is to convert to a rectangular equation. So find rectangular equation, and if that is a function that you are familiar with, you could also go ahead, you could graph it from there. Okay, so we're going to go ahead and just use this as an opportunity to practice the skills that we kind of talked about in example 1. We're going to take our x equals 2 sine t equation and our y equals 2 cosine t equation, and we're going to work to go ahead and isolate our trig functions, right? Our trig expressions, the sine of t and cosine of t. So we know from here that we get x over 2 is equal to sine of t, and we get y over 2 is equal to cosine t. Okay, reminder that we relied at this point on this trig function, or this, trig identity, the Pythagorean identity there, with sine squared t plus cosine squared t equaling 1. So I'm going to go ahead and introduce that here and square both sides, which will give me of this equation x squared, or x over 2 equals sine t. That'll give me x squared over 4 equals sine squared t, squaring both sides here, so I could kind of detail what I did a little bit better. That gives me y squared over 4 equals cosine squared t. So leveraging that Pythagorean identity, instead of writing sine squared t plus cosine squared t equals 1, I can go ahead and actually just make that substitution right away and say that we have x squared over 4 plus y squared over 4 equals 1. Now, this might not be something that you're super familiar with, graphing, right? Maybe it's been a minute since you've dealt with conics. But what we could do is go ahead and actually multiply both sides by 4 and find that x squared plus y squared equals 4. And this should hopefully be a little bit more approachable, right? Hopefully you recognize that this is a circle with center center at 0, 0, and radius of square root of 4, or 2. So if you look up here at our graph that we did the first way, we should be seeing a circle with center 0, 0 and radius 2, which we definitely have. Okay, so again, a couple options there. Either one is fine. I wanted to talk about option 2 here, just to kind of revisit this conversion, right? This type of conversion here that's relying on that Pythagorean identity.